This is my first time at MetalCon, and I'm going to describe to you some aspects of acoustics, some of the history, demystify a few things, and really get to the point of why I'm here today. Let me start by just saying that my business partner and I, Micah Silver, we together have about 35 years, I think, of experience in the acoustics industry. We're relatively new to the metal building portion of this. And what we noticed over the years, and recently in particular, is that there seems to be an aspect of this where acoustics could be given a little bit more attention. We're going to get to that as well. Micah and I essentially met through this project. This is the Experimental Media and Performing Arts Center in upstate New York. It was designed by Grimshaw. It opened in 2007 or 2008. I was part of the acoustics design team. Micah was one of the founding curators, basically, of the program there. The point is that we're both experts in sound. We're experts in acoustics and architecture, and we're a resource. We want to help the design community understand sound, understand acoustics in the best way possible, because we want to help make our built environment sound better. We think that some of the reputation that metal buildings have acoustically may be a little bit unwarranted, and we see very clear paths to making that better. So I'm going to start with the weirdest slide. This is the weirdest slide of the whole group. This is an acoustic testing chamber. Every product that you see in acoustics should have been tested in a chamber, something like this. This photo happens to be 100 years old, so this is obviously a little bit dated, but we actually still use this same chamber today. It's just that our technology has changed. But one of the reasons I love to talk about this slide is that it really helps us understand some important things about acoustics that I think are often not talked about. In particular, that everything has acoustic properties. Everything has acoustic performance, acoustic behavior. It's really just a matter of degree. And this image helps us with that because we are not only still using this room today with newer technology, but our process for testing things is essentially the same. This room is extremely reverberant, something like 6 or 7 seconds. That means that if you drop a wrench in this room, which I have done before, if you're talking in this room, if you're singing, if you're making any kind of sound in this room, it will last for a full 6 seconds before it dissipates. In a room like this, that is intentional because that helps us to test products, but you wouldn't want this in a lot of other spaces. But the idea is that you essentially fill this room full of sound, and you measure how long it takes for that sound to decay. You measure its reverberation, and then you put the thing you want to test in the room, and you run that exact same test again. And so you have 2 tests, one with the sample you're interested in and one without, and you can mathematically compare those 2 things and back out how much that sample is absorbing. So even 100 years ago, when the room looked like this, we still tested basically the same way. The neat thing about this photo, or the 2 neat things, are that to create the sound, we didn't have loudspeaker technology like what we have today. So we had to use an organ. That's literally just air being forced through those pipes to create the test signal. And we didn't have microphones that were sensitive and reliable like we have today. So somebody had to sit in the room while the test was running. Their ear was the microphone. They were listening to how long it took for the sound to decay. But their body and their clothing would actually affect the test because everything has some kind of acoustic influence. So in order to make sure that the body and the clothing didn't change the test from day to day, they built this weird box for the person to sit in. So the only purpose of the box is to make sure the presence of a human being is consistent day after day. If we jump ahead about 100 years, this is the same room, exactly the same room. You can see the microphone here that we use for the test instead of the person in the box. And this is a testing sample. These are actually made out of glass, and we're not really going to talk much about glass today, but I'm going to at least talk about it a little to make a point, which is that this is a research project that I've been working on where we take auto glass, flat auto glass, and we shape it so that it has acoustic properties that we want. And glass is one of those materials, it's similar to metal in that it has something of a bad reputation in architecture acoustically. But the point is that if you know the material, you know how to shape it, you know what that will do acoustically, and you can take advantage of those properties. So we're going to come back to this. But this is precisely the same room. It's been being used for over 100 years. This is outside of Chicago. If anybody is ever in Chicago and wants to take a little field trip, this room is, this reverberation chamber that we test everything in is west of the city. It's a fun little field trip. There's a lot of interesting history out there. And we actually built this glass wall. Again, we're not going to spend a whole lot of time on glass, but just to make a point, if you know how to shape something, you can understand its acoustic properties. This is a glass wall that has very distinct acoustic properties, very intentional. And actually, we're going to stick with glass for one more slide. This is also that same room, and these are empty beer bottles. And I don't know if anybody's surprised, but beer bottles actually absorb quite a bit of sound, at least at a very particular frequency. And so I'm sharing all of this in part to, we want to break free from this idea that acoustics is only about the products that are labeled acoustic. Those products are labeled that way for a reason. They have more influence than products that were not, or surfaces that were not engineered to be that way. But you could also think of this in a more cynical way. This lab would let you test anything you want. You can send them anything you want. They'd be happy to let you pay them to do it. And then just one more slide to take this a little bit further. Any guesses as to what this material is in this room? This is Bell Laboratories, built in the 1940s. It actually happens to also be glass. It's fiberglass. We think about fiberglass as being a very different material from plate glass because it looks so different and its behavior is so different, but it's fundamentally the same substance. And so a lot of the acoustic products you see, they essentially take a substance and they put it into a configuration that makes it work acoustically in a more substantial way. By the way, this floor is not visually reflective. That is a wire mesh grid that the person is standing on because they want to just absorb all the sound for experiments. And so those are actually wedges that you can see. The floor is covered in them as well. So let's get down to the next thing. So the idea is that if you know how to configure certain materials, you'll get certain acoustic performance out of them. This is really where the entire acoustic product industry comes from. I'm going to play this video. This is a video of shredded water bottles that is being turned into a felt. So this is a couple of minutes long. We see felt everywhere these days in architecture. It's really having a moment because there's a lot of great things about it. It's durable, it's machinable, it tends to be fairly rigid, it meets flame resistance criteria. It has great acoustic absorptive properties. So even though I've shown a couple of examples of things that have acoustic properties that are maybe unexpected, something like beer bottles, you don't really want to treat a room with beer bottles. You probably want to reach for something that was designed to do a little bit more. And this is showing some of that process. You can really think of it as like, I mean, these are really tiny fibers. If you look at felt closely, it's incredibly complicated, right? It's porous. It's taking a material that's happy to be in that fibrous form, and it's making it into like a sheet that can be applied and used for a particular purpose. Okay, so next we have a series of a few slides that are just text. And this is the only equation in the whole thing. But it's kind of an important equation to relate acoustics to our experience. So this is from way back. The Sabin equation is from way back in the 1890s. It was even before that laboratory photo that I showed you. It essentially says that reverberation time is equal, forget about this K, this is just a constant, as long as your interior space is similar, if it's a typical temperature and humidity, it's not really going to change. So our interior spaces generally stay pretty stable in that range. So K is always the same. The volume of the room is here, and then the total absorption in the room. This is something we're going to dig into a little bit deeper. A is the total absorption. So what this means is a couple of things. Number one, since volume is in the numerator, the bigger your space, the more reverberant it'll be. And that is something that I think we've all experienced, maybe we understand intuitively. The reverberation time in the space we're in right now is quite a bit longer than if this were a much smaller room, even if it had the same materials. The other thing is that the more absorption you put into the room, the lower the reverberation time is. That also should be pretty intuitive. And so from the standpoint of getting the right reverberation time in a room, you really only have two things you can change. One is you can change the size of the space, and two, you can change the absorption. And so you can kind of see how the product industry evolved into this restraint, right? Or these constraints, because you do have some control in the design process sometimes over how large a space is. You can determine the ceiling height, but we all know that cost and function generally drive those things. Put another way, I've been doing acoustics consulting for 20 years. I think I've only been involved in one project where we actually changed the volume of the room in order to change the reverberation time. And that was a weird one. That was a concert hall in London where we actually opened up the attic space because we wanted a longer reverberation time. That's also unusual. But we open up the attic space, increase the volume, the reverberation time goes up. But really almost never, especially if you're trying to reduce reverberation, you're not going to find clients who want to reduce their ceiling height in order to do that. And so practically speaking, adding absorption is really the only way to go. You have to be able to add absorption to the space. And we already learned that basically everything has some absorption to it. Furniture does, people do, anything with any kind of shaping does, but it tends to be relatively mild in effect. Anyone who's ever moved out of their apartment and empty the space out and notice that it sounds different, it's very reverberant when you do that, and you probably aren't moving out a bunch of acoustic panels, right? It's all of the other stuff. It's your furniture and your books and your objects. All of those things add up to significant effect. But the problem is that the simpler your buildings, the more spare they are. If you just are going to do a big open space with blank walls and a blank ceiling, you're going to get a large reverberation time. It could get in the way of the function of that room, and you're going to have to add some absorption to get there. That's the basics of it. Does that make sense to everybody? Yeah? Okay. I don't know what the composition of the room is, but do we have architects here, interior designers, people in the metal building industry? Have you heard of NRC, noise reduction coefficient? It's usually, if you haven't, when you pick up really any acoustic product, whether it's a ceiling tile or a wall tile, it's going to have a rating. It's going to have an NRC rating. And this NRC stands for noise reduction coefficient. And it is the worst name for any parameter I've ever seen, I think in any field, but definitely in acoustics. We really screwed up, and I'm not exaggerating, in the 20th century when we named this NRC, because it's confusing. For those of you who are in the more engineering fields or you like math, I'll just tell you that when you dig into the math here, it's not even a true coefficient. So coefficients generally go 0 to 1, and they generally can't go above 1. NRC is not really a true coefficient. Let me explain it this way. When you take a sample to a lab like what we showed, and you have it tested, they're going to tell you how absorptive that sample is, and they're going to tell you that in a Sabin. So we're gonna just talk about these three: NRC, Sabins, and area of coverage. The Sabin is the basic unit of acoustic absorption. Everything has Sabins, just like everything has pounds, right? These headphones, they don't weigh very much. They have a very small number of pounds. The table has more pounds. This building has more pounds. You get it. You can measure anything for Sabins too, and it turns out that the fuzzier stuff, the more porous stuff, felts, fiberglass, velour, those all have more Sabins than the hard stuff that's non-porous, like tables and gypsum board and glass. So when you send something to the lab, they tell you how many Sabins it is, how many Sabins your sample is. But if you're selling a panelized product like ACT, you're selling wall panels, ceiling panels, the smart thing is to take the Sabin count, how absorptive is your sample, divide it out by the area, and figure out how much each square foot is bringing, right? How many Sabins does each square foot have? That is what NRC is, and that's why I say it was a terrible mistake to call it NRC. We should have called it absorption per square foot, and this is the best way to think of it. So this is probably the most, if for anybody who's buying acoustic product to fix a room, this is probably the only real takeaway that you need from this whole thing, is that when you pick up a sample of anything and it says NRC 0.8 or NRC 0.5 or NRC 1.1, what it's telling you is how much each square foot is doing. That's all it's saying. So of course, there's another step, which is how much do I need in the room, right? Because you need to get a certain amount of absorption in the room. You now have a product that tells you how much each square foot is doing. It's a relatively easy calculation. It's something I can't really explain, but for some reason, through the 20th century, acoustic products just took on this whole thing where people don't recognize that other things have acoustic effect, and people tend to think that higher NRC is better, and they forget about the area part, the square footage part. Higher NRC is better in the sense that you can use less of that material to get the same job done, but if you like a lower NRC product, no problem, you just have to use a little bit more. You just can't lose sight of the idea that it just means what each square foot is doing. So if that's the only thing you take away, this is what I encourage the entire design community, since it's too late to change this name. When you see NRC, just think Sabins per square foot. So in the description to this is, I think, the last text slide, and then we've got a few more interesting slides. In the description of this, I mentioned that we're going to compare acoustical metal decking, banners, baffles. There's actually acoustic lighting now, clouds, panels. I'm actually going to gloss over that a little, because what you really need to know is that all of these products just bring Sabins to the room, and any manufacturer that's worth working with will have had their products tested in a lab like we showed you at the beginning. And so they often report their data on their website. You're welcome to ask them for their actual lab reports if you want. It's not exciting reading, but it's actually a really great test to see if you can trust a manufacturer. Just ask, like, can you send me the lab reports? There's nothing proprietary in any of them. They should happily send it to you. These labs are independently run. They meet all the standards. As a consultant, this is how I navigate this, because there's a lot of products out there. They all have different ratings. All I need to do is make sure it was tested in an accredited lab, and I can compare them all to each other. So the way that we would fix a typical room, and we're going to get to a case study, is we figure out what its reverberation time is. We might calculate it, we might measure it, we might simulate it. We got a lot of ways to do that. We figure out what it is, and then we figure out, is it too high? Because it often is. And then using these tools, we can just figure out how many Sabins do you need to add to the room to get it where it needs to be. It's really that simple. And then you can look at all the products. How many Sabins per square foot do they bring, AKA NRC, and you can get the room where it needs to be. So there's no need to say that felt is better than acoustical metal decking, or acoustical metal decking is better than felt. The point is what works for the visual needs of the project, what works for the schedule, what works for the budget. As long as you're getting enough absorption in, it doesn't matter to me, the consultant. Are there any questions or anything at this point? I think we've got some time at the end, but it's a small group. And does anybody have any burning questions to ask? No? All right. We'll have a little time at the end too. I think my whole presentation is like 40 minutes, so we're actually nearing the latter parts of it. I just wanted to talk a little bit about metal buildings in particular. Now that we know that basically everything has acoustic properties, we've looked at glass, when we've looked at resin or PET, and of course metal does too. It turns out that the configuration of that metal is really what matters the most. This is the oldest truly metal building that I've ever been in, and it wasn't intended to be a building. This is the tank in Rangeley, Colorado. Is anybody familiar with this, or have you ever been there? Rangeley is a very small place. I think it's a couple thousand people. And this tank was apparently built in, I think, the mid-1800s. And it was built elsewhere. Its origins are a little bit mysterious, but it was shipped to Rangeley at some point to be used to store water. And they realized that the ground that was underneath it was not strong enough to hold it if they were to fill it with water. So it just sat vacant for decades, many decades, until the middle of the 20th century, and kids found their way through like a portal on the side and realized that it just had these incredible acoustic properties. They would just go in there, and the sound that you would make in there would just linger for, it actually has a reverberation time of about 30 seconds, which is just hard to believe, right? And what I mean by that, really, if you make a noise in there, you will hear that noise bounce around for 30 seconds. It's incredible. And the kids hanging out there and partying in there turned into interest from others, and suddenly musicians are playing in there. And then eventually they turned it into a nonprofit, and they built a recording studio next to it, and they produce music there. It's very, very cool. And this is one of the things. So metal has a reputation sometimes of being bad acoustically. It depends on the configuration, and it depends on what you're trying to do with it. If you want to, they recorded a Beethoven record there, and they had to play it real slow so that everybody could hear the changes. So, there isn't really absolutes either. I'd say for most of architecture, you don't want a reverberation time like this, but every once in a while, maybe you do. That's probably the most extreme metal building I'm aware of, and also one of the oldest. And then this is yet another one. This is a more recent one, of course, and I know that I'm learning a lot about the history of metal buildings. I know that a lot of it is connected to World War II and Quonset huts, very quick and efficient buildings that were made out of metal. This is a development in Detroit. I live in Detroit. I don't live in this development. But this is called True North, and they made these Quonset huts maybe 10 years ago and fit them out for tenants, so you can rent, you can live here. Detroit has a lot of vacant land, and so people do interesting things with it. Things like they farm it, they plant trees, they build things like this. It turns out that the acoustics of these are actually not as severe. You can see some similarities between this and this, right? You can see the cylindrical form, but it turns out that when you take away that smoothness, when you start to make the shaping more complicated, it actually gets a little bit better acoustically. So these are better, even if it's just exposed metal. It's essentially the same material. The reverberation time goes down a bit. And what that means practically is that you'd need to add fewer sabins to the room, in the terminology we've just been talking about, to get these under control. And honestly, because it's Detroit and it's cold there, in most of these, they actually have a layer of plywood or gypsum board on the inside anyway, and it hides the metal, but you get the point. And then, of course, this is a space that it's not a fully metal room, but this is what we more commonly see in the metal building industry. This is actually a gymnasium in Los Angeles. And this is a case study, so we're going to talk about this and how we fix a room like this, and that's going to be the end of the conversation. We'll open it up to some questions. But remember when we increase the complexity from this to this, the reverberation even goes down, and that's without even adding anything. The same thing happens when you go from here to here. That's a complicated looking ceiling, geometrically, right? It's got a lot of shaping. It's got a lot of form. And often you end up with things like ductwork and everything. It turns out that all of that stuff is beneficial. It all helps a little bit. It's not that metal isn't doing anything good acoustically. It is, but it often doesn't get you all the way there. So if we look at this one, they embrace the long reverberation time. In this one, not a good thing. I think the reverberation time was 8 seconds or something like that in this room. When I say not a good thing, I mean they use it for community events. They want to be able to talk with a microphone. They want people to be able to gather, and the room just gets too loud. We are experiencing something like that here, and there's an energy to this because there are people here, and in some ways it's nice, but it doesn't make communication easier, right? It turns out that when you put a bunch of people in a space that's really reverberant and they all try to talk to each other, they have a tendency to feel like they're not being heard, and they all try to talk a little louder, and then that louder talking reverberates for too long, and then they try to talk a little louder, and this is why some restaurants and bars, you just can't hear anything. Everybody's shouting. Turns out if you get the reverberation time right in those spaces, then everybody feels like they're being heard, and they just talk more quietly. It's a psychological effect. So the stuff we add to rooms to reduce reverberation doesn't directly reduce the loudness when it comes to people. It just makes their environment healthy and comfortable, and they don't have to talk as loud, and they generally don't. So in a space like this, we recognize that the metal ceiling's already doing a lot, and we've got this extra visual aspect, which I don't intend to get into much detail on, but of course, if a building like this was made 50 years ago or 60 years ago, there's a good chance it would have had an ACT layer covering this up. There's a good chance that they would have wanted something that was more finished looking, and that's of course changing, or it has changed already. This is a beautiful looking ceiling if you ask me, and I know a lot of people who agree with that, and it's more budget conscious than adding a whole nother layer. But what we lost when we took away the ACT layer were all those Sabins that the ACT layer was bringing. And we can recognize that the complexities of the metal are doing something, but it's not quite doing enough. And this room was just too reverberant, so we needed to help them fix it. And one of the things I have dealt with in my whole career with acoustics is that people just don't generally want to see. They haven't historically wanted to see what you're putting in the room. In other words, the visual impact of adding all this absorption is something that clients, building owners, architects all tend to want to avoid. And that has changed a lot in the last 20 years. And when you look at a ceiling like this, if this is meant to be seen, then the question is, what can you add to it to bring the reverberation down that's not going to take away from how it looks, that's going to integrate into it? So I have a detail here. I don't remember exactly. I've never given this talk before, so I don't remember the exact order of the slides. But this is what we came up with for this space. You can see this is just a perspective view, an axonometric, I think, technically from underneath. You can see the metal decking, and then there's an airspace, and then you've got a layer of felt. And one of the real challenges, this is a sprinkler head. This is a retrofit, so we have to make sure that whatever we put in doesn't block any sprinklers. There are local codes. This one is in Los Angeles. The restrictions out there as far as flame resistance and fire code are probably as stringent as just about anywhere. Maybe Chicago's more stringent, but this was a bit of a challenge. How do we get, you can see the section here, how do we get the absorption in a way that doesn't interfere with the sprinkler coverage? Also needs to meet flame resistance, of course. And there's this added thing, so this is kind of a neat thing to also keep in mind. Remember, NRC is really just absorption per square foot. For absorptive materials like felt, if you put a deeper airspace, your NRC actually goes up. Acoustics is about configuration, not just the material that you're buying. And so we wanted, in order to not have to cover the whole ceiling, we wanted to keep this airspace as large as we could so that each square foot was doing more, but also not interfere with this. It was just a little bit of a balance. Another nice thing that those airspaces are helpful. So for metal decking, you do have some airspace kind of built in, right? That structural corrugation not only is visually interesting, but it also adds acoustical value if you know how to take advantage of it. So we also did some calculate. Actually, we did a measurement in this one. Like I said, we can measure, simulate, or calculate. This is kind of small, but I'll just tell you, this is reverberation time. So for a gym like this, higher is worse, lower is better. This is 4, 6, 8 seconds. So this is more reverberant than the reverberation chamber we showed you, more reverberant than the testing chamber, which is clearly not a good thing. So the pink is the existing. When they built the space, that's what it was. The acoustics were so poor, the reverberation was so long, it was getting in the way of the function of the room. And we did some calculations to figure out how much of this stuff they need in the room. In the language of what we've been talking about, reverberation's too high, they need to add some Sabins. We figured out how many Sabins they needed, and then based on the product that went in, how many square feet was needed. This acoustics has a reputation sometimes of being really mysterious. It's really not. This stuff is very mathematically determined. The hard part is the integration. The hard part is getting, I think, the owners to recognize that this stuff matters and that you're going to generally need a decent number of square feet to get the job done. So this is the end result for this particular installation. Used a felt that is essentially corrugated to echo, that's a weird choice of words for this, but the visual nature of what was there. So we largely kept the visual nature of it. There was no change in the sprinkler systems that had to happen, nothing like that. The reverberation time dropped down to about 2 seconds. The client is thrilled with it. We also looked into adding stuff to the walls because that was an option. But we determined that we didn't need it in this case. So that's one important thing. This analysis step, understanding how Sabins work, how reverberation works, it allows you to really dial this stuff in without overdoing it. And if you really look, this is intentionally integrated, but if you really look, you even see gaps and you see areas where it didn't make sense for them to add the felt. This is not 100% coverage. It was really brilliant, I think, of the ceiling tile industry to just design a ceiling system that encouraged you to just do the 100%, the whole thing, basically. But that actually was more Sabins than you typically need. And now that exposed structures are becoming more popular, we can actually dial back the total amount. I want to say this was 60 or 70% coverage. Relatively easy to install. They did do some kind of a spacer system, so they would just, shoot the, it was some kind of channel, hat channel, I think it was, into the deck, and then they just attach the acoustic panels to that. And that is actually the end. That's what I wanted to talk about. So if anybody needs credit, so I obviously kept like any kind of like brand stuff out of that just because it's supposed to be for credit. But I will show the last slide, which is that this is basically the reason that we're here. We are in booth 503 if you want to talk to us, if you have any questions about acoustics. We know quite a bit about this stuff. So it's nice to be here at MetalCon. Thank you for coming and giving your attention to this. Are there any questions from anybody? Anything you wanted to know about acoustics? Oh, we got a mic coming.
Hi.
Well, thanks. I was kind of curious, like, how do you determine how many Sabins you're going to need in the space?
Yeah, how do you determine how many Sabins? I glossed over that a little bit. We start with reverberation time. Reverberation time is not the only thing that matters in a room, but it's a primary thing, and it's a really good indicator of what's going on. So in a room like this, we measured it, we got a certain reverberation time. We then basically check our best practices and our standards in the acoustic industry that tell us what should that reverberation time be. And there's a discrepancy there, of course. In this case, it was about a 6-second discrepancy. We can then use that equation that I showed, which relates reverberation time to room volume and absorption, because the volume of the room hasn't changed, and we just back out how much absorption that discrepancy is, if that makes sense. So in other words, we calculate it. Any other questions or anything?
My name is Vince Sagan. I'm with the Metal Building Manufacturers Association, and so if you're designing a metal building and acoustics is a consideration, the MBMA has a free download of an acoustics guide of various assemblies that have been tested that have OTC values, STC values. So I just wanted to make people aware that that resource is available.
Yeah, thank you. And maybe I'll add to that because you mentioned STC, for example. This talk was essentially about reverberation control, the interior finishes of a space. Another challenging aspect of acoustics is sound transmission, say across wall or floor and ceiling systems. So I'm glad that you brought that up. That has to do with the construction of your wall, how well sealed it is, how massive it is. So you also want to make sure that you identify the type of problem you're trying to solve before you start to reach for we see too many people reach for felt, for example, when they're really just trying to stop somebody next door from hearing them, and they might need some silicone sealant for that, right? So you just keep in mind that these different parameters, if you've heard of them, they go on to NRC, RT, reverberation time, STC. We have different parameters for each different thing, and they usually require different approaches. Any other questions? Okay. Well, great. We love to talk about acoustics, so please find us if we can help. I didn't mention this part. Acoustics can get pretty complicated, especially if you're doing like a recording studio or something. So sometimes you really just have to hire somebody. For a lot of spaces in this category, the similarities are greater than the differences, and we've decided that at least for now we're just going to be offering free analysis if anybody's interested in fixing their room or their space. And because of that equation, where volume and absorption are the only two things that really come into play, this analysis does not have to happen after your building's built. It can happen when it's in the design stages. We need to know the material of the room, the dimensions of the room, and what you're going to use the room for, and we're happy to do that part for free. If your project is complicated enough that you need to hire somebody to be a part of your design team, we could also help you find somebody who does that sort of thing. So maybe I'll leave it at that.